All right, what is up? Today, right now, I'm going to talk about question A53. And the, we're given a bunch of starting position of a car and also a bunch of speed for the corresponding car. And we have a target that all the cars needs to be arrived at. And we are trying to find, and a car will be slowed the car's arrival speed is dictated by the slowest car before it. So if in this example, car 8 and 10 will meet each other at time 12, and car 0 doesn't catch up to any car, so it's a fleet itself. And car at 5 and 3, which is the last two, they will meet each other at time 6. So it will be a total of 3 fleets. And the idea here is to calculate the time because they're all um, started. They will start moving at the same time. So the one constant that we can find is the speed of the of a particular car. For example, for the car at position 10, um, its distance between 10 and 12 is 2. And to cover that distance, the speed is 2. So we only need, so this car only needs 1 unit of time. Okay, so distance over speed is equal to time. So you only need 1 unit of time to arrive at the destination. And for car 8, it's 4 units away from our target 12, and the speed is 4. So for car 8, it also only needs 1 unit of time to arrive at the destination, which makes them a group. And then for car 5 and 3, 5 is 12 minus 5 is 7, and over 1 is 7 unit of time. And for car 3, it's 9. 9 over 3 is 12 minus 3 is 9. 9 over 3 is another 3. So 1 is 7 and 1 is 9. And because 3 is actually further away than 5. So 3 is 3, but 3 speed is faster than 5. So 3 will eventually catch up to 5 because the time it takes for 3 to arrive is only 3, but for 5 to arrive is 7. So 3 and 5 will become a car fleet. And car 0 is going at a speed of 1, and it takes car 0 12 units of time to arrive, um, which makes it um, a group of its own. And this makes us realize that we need to sort all the cars based on its starting position. So and then we can calculate that we can maintain a slowest car speed, and we can scan starting from the car that's closest to the target. And by doing that, if we have encountered a car that is slower than the current slowest car, we know that um, that car will form a fleet um, on its own because all the cars before it will form a fleet, and it will and we can update the slowest car time again. And if we have seen another slower car after this current slowest car, that means we have found a fleet again. And that's how we can compute the solutions. So first, what I'm going to do is I'm going to sort all the cars based on its starting position. So let's say a fleet. First, I will need n is equal to position dot length. So this data structure will allow me to store the position with its speed without and even after sorting it based on its position. So I can do arrays sort uh, fleet, and we'll give it a comparator. We'll return integer.compare B0 and A0. This way, um, all the cards that is closest to our target will be first, which is the bigger numbers will be first. And then we can start to iterate through the entire fleet. So, and oh yeah, we also need to keep track of slowest time and also the amount of fleet, and starting at 0. So if yeah, so first we need to calculate the time, which is in a form of double because we might have we might have decimals. So I will be our target minus our fleet I and its time divided by its fleet and its speed, which is at index 1. We want this to be double, so our result can be double. And if this time is taking longer than our slowest time we've seen so far, we will need to increase count by 1, and we also need to maintain the slowest time, which is at our current time. Slowest time needs to be double because we're assigning a double to it, so that might be the case. And then after iteration, we can just return the count. Okay. I cast this entire thing to double again. Let's see about others. Okay. Let's do some debugging. So first we sort it by its starting position, and then we want to find let's just save. Oh, um, so if I'm trying to think what is our problem here. So if our current time is slower, is taking longer than our slowest time, that means we have found a fleet. So, and we're sorting it based on the closest Okay. That shouldn't be any problem. Let's put some breakpoints and do debugging here. So, oh, okay. So first, we need to populate the fleet, of course. We need to populate the fleet with the speed, which is fleet. First is position, so we'll have position I, and also speed I. Position I, speed I. All right, cool. Let's see. All right. All right, cool. So for the time complexity, it's detected by the sorting algorithm here, so it's n log n. And the space complexities, if we're doing sorting in place, we can do the only extra space that we're using is the fleet algorithm data structure that we use to store the position and speed pair. So split, and that's at most length n. So the space complexity is O(n), and time complexity is O(n) log n. All right, thank you.